Okay, welcome to our second lesson on magnetism. And this is about how to generate electricity using magnets. In fact, you obviously have electricity running to your house. You turn the lights on, flip the switch, comes through the wires from the power plants. This is the way they generate electricity in the power plants using magnetism. So figuring out what we're going to learn today was of an enormous consequence to humanity, figuring out how to generate electricity from magnets. Okay, so before we go into how it's done, you need to learn a concept of flux. What is flux? It's the amount of magnetic field that penetrates through an area. And the symbol for it is a Greek letter, phi. It's like a circle with a line going down through it. And B subscript, because B is the symbol for magnetic field. And what it is, flux is the amount of magnetic field that's perpendicular to the surface of the wire loop times the area of the loop. I have a couple diagrams here. So here's a wire loop, copper wire. If magnetic field were coming straight out of the paper like this, because maybe I have a bar magnet underneath this block of wood, and so the North Pole is coming, sending magnetic field out this way. If I put this wire loop like this, I do have flux because the magnetic field lines do penetrate through this area. They come out through this area. That means I have flux. If instead I put the bar magnet over here, so my finger here is the North Pole of a magnet, well, maybe I have this little paper here. So North Pole, then the magnetic field lines would not generate flux because they would run along the surface. They wouldn't poke through it. So there's no flux here. Even though I have magnetic field and I have a wire loop with an area, there's none of the magnetic field is perpendicular to the wire area. So no flux. So here is the big idea named after Michael Faraday. Faraday's law. The voltage produced in a wire loop is equal to the change in flux per time. So it's kind of like a little like velocity per time is like how fast you're moving. This is how fast the flux is changing. Change in flux per time. There's also a minus sign there, which is more information than we need. So here's some examples. The first example, you have a light bulb here. A light bulb, if you look on your reference table in the Regents curriculum, is a circle with a spiral through it. That spiral represents the filament of the bulb. And I have a wire loop just like this, but I've got a bulb in there. And I have a magnetic field that's constant. So there's no current in this, and the bulb does not light up because there's no change in flux. I have flux, but it's staying constant. Unless I change it, then I get voltage. Okay? In this case, if I increase or decrease the magnetic field, so maybe I've got a bar magnet behind this wood, like, point magnet, and I take the bar magnet away. Or I bring more magnets closer, so I get to make B bigger or smaller. Then I get current because I have voltage in the loop, and the light comes on. Okay. Now, technically, the amount of voltage produced would be so small in just a wire loop like this, then you wouldn't see the light come on. You would have to have a very sensitive voltmeter to see that voltage produced. But nonetheless, that's the concept. Changing flux per time gives you voltage. Here's another way. So I have a constant magnetic field and I have a wire loop like this. So I have flux, magnetic field coming out of this surface. If I take this and while the magnetic field's coming out of paper, I swivel this up like this. So I'm not changing the magnetic field. All I'm doing is turning this. So I have flux because the magnetic field's coming out of it. And then I turn it like this and I don't have any more flux because the magnetic field is running along the surface. None is going through. So I go from flux to no flux. That's a change, and that would, while I'm turning the thing, create light, create voltage. Okay? Only while I'm turning it. Once I stop like this, the light goes out because, again, I'm not changing the flux anymore. Another way to generate, this is more popular in the Regents. They don't really go so much with flux, but I put it there because I think it's important to understand. This is the actual principle of Faraday's law. But the way the Regents likes to illustrate this concept is with like a wire slicing magnetic field lines. That also generates voltage. So here I have the wire like this, magnetic field's coming out of the paper. You see the dot with a circle, that's arrows coming out of the paper. And if I move the wire this way, what I'm doing is I'm slicing the magnetic field lines. So imagine like I'm cutting through them. I cut through magnetic field lines, or I cut through them that way. Either way I move this, I get voltage. That's why I put yes, yes. If I have the same scenario, but I move the wire up or down like this, then I'm not slicing the magnetic field lines. See how these field lines are remaining intact? I'm not slicing through them like before. So since I'm not slicing through them, then I don't get any voltage produced. Another situation, so no, 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 whether I move this way or actually up out of the paper or into the paper, I am not slicing through the lines at all, okay? I'm just going like along them or along them, okay? So either moving this way, this way, this way, this way, no, 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 okay? Another possibility is that I have a magnetic field running along the paper, so maybe I have a bar magnet like this, right? Making magnetic field like that. And then I take the wire and I move it this way or that way. No, no, because I'm not slicing through the magnetic field lines, I'm just running along them. Or I move this way or that way. Same thing, I'm not slicing through the magnetic field lines. No, 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 for all these various motions. If here instead I take this wire and the magnetic field lines are going like this and I pull it up or down, now I'm like, imagine these magnetic field lines like spaghetti strands. I cut through them, I cut through them. No matter which way I move this way, then if I push the wire down through the table or lift it up off the table, yes, yes, I get voltage. The last thing that I want to mention is what is called a transformer. A transformer, when electricity is transported over long distances, it's transported as hundreds of thousands of volts. If you put that into a house, all your appliances would get destroyed. You could also get electrocuted by the electricity jumping out of the wires through the air and into your body. So they have to make the voltage go down from hundreds of thousands of volts. That's where you see those giant towers of wires. They have to reduce the voltage to make it safe to go into a house. That's what a transformer does. But it only works with alternating current, AC, alternating current, which is the household electricity that we have in our house wires. Not battery electricity, which is called DC, or direct current. Why? Direct current flows and stays steady. And if the electricity flows and stays steady, then there's no change in flux. The electricity has to be oscillating to create an oscillating magnetic field. That's one of the things we're actually going to learn about in the next lesson, that magnetic field is created also by electricity. We saw that also in lesson 1 with the electrons orbiting. So moving charge creates magnetic field. So what you do is you just have a coil of wire, 2 coils of wire next to each other, and there's usually iron or some kind of magnetic material that passes through the coils. And you have a different number of coils in each coil. What I mean, a different number of wraps. So this can go around 100 times. Maybe there's 1,000 loops of wire on this end. And what that does is it makes the voltage increase. This is where you put the electricity in, like maybe you plug this into your wall, and these wires go output to some device. And what that does is by making 10 times as many coils here, it means that in the end you get 10 times as much voltage as the 120 volts of the wall outlet. Simple ratio tells you how many volts you get out. You can also make the voltage go down to a lesser voltage. So here we have the input have 1,000 coils instead of 100 coils. 1,000 coils, and then on the output end we've got 100 coils instead of 1,000. So this plugs into your wall, this coil. This coil goes to some device you're trying to run. And then what happens by having fewer coils instead of more on the output, you get 1/10 the coils, 1/10 the voltage. So that's the beauty of alternating current, like we have in a wall. You can step up the voltage or step down the voltage just by having wire coils, a set of wire coils next to each other. We call it a transformer. So that's lesson 2 of magnetism. Primarily what the Regents really emphasizes is this right here. This is all background stuff that's actually more solid physics, which I included just so, we get a thorough lesson in this very strange topic of magnetism in the regions, which is just a very quick 2-3 days of just some facts about magnetism, unfortunately really oversimplified. So that's lesson 2. Again, do the homework. The answers should be there of the PowerPoint, so you could check your answers right as you're doing the homework, and then report in the Google Sheet anything you would like to see solved out, and then I will put a solution up for you. Okay, so see you in the next lesson.